Hi, I'm Angus Brayne from BenevolentAI, and I'm going to present our work on masked language models for contextual link prediction. This work was done in collaboration with Maciek Wiatrek and Dane Cornel. So, to introduce the problem, I'm going to start with this question. How can we represent complex facts within the confines of a knowledge graph? Consider this example query. Who did the USA elect as president in 1960? Most knowledge graphs use a simple triplet format to represent this. USA as the subject, elected president as the relation, and mask as the predicted object. Some predictions might be Abraham Lincoln, Barack Obama, John F. Kennedy, etc., given this representation, because in 1960, the context here is missed off. These standard knowledge graph approaches struggle to integrate this context in 1960 and must be carefully amended to deal with it. So this context could take the form of a location, a type, a time, which are all very common in facts. We call these higher order relationships that include more context than the two entities in relation n-ary relationships, or hyper-relational facts. 1960 here, which is a numeral, is often referred to as a literal because it exists on a continuous scale. So where standard knowledge graph approaches struggle to represent this context, natural language formulations deal with it easily. As you can see, we can just increase the length of the string to include the additional information here. USA elected president mask in year 1960. So to answer that original question, how can we represent complex facts within the confines of a knowledge graph? Our approach is to use natural language instead. An additional benefit of using natural language is that huge natural language corpora may also be utilized. So let's dig into this a bit more and talk about the two problems that we're looking to solve in this paper. The first problem is representing literals. Literals can't be efficiently represented as discrete graph entities and are typically ignored by the standard methods. Literals include numerals like dates that exist on a continuous scale and would cause an explosion in graph entities if included. Literals, on the other hand, are represented efficiently by language models. For example, word piece tokenization reduces literals to chunks of commonly shared characters in order to avoid an explosion in number of tokens. HyperELK, which is the model that we propose here, is the first approach to n-ary link prediction that leverages literals in n-ary qualifiers. The second problem that we're looking to solve is circumventing the knowledge graph. Construction of partially complete hyperrelational knowledge graphs in new domains is expensive and time-consuming. Now that we have the ability to use external natural language corpora, we can pre-train on entity-linked corpora, and that gives us the ability to circumvent the need for any training knowledge graph. HyperELK is the first approach to n-ary link prediction that does not require any n-ary training set. So let's dig into the details of the method a bit more closely. Our method consists of three stages: pre-training, fine-tuning, and evaluation. During pre-training, we pre-train the language model to predict unique identifiers of a masked entity within a sentence. This sentence comes from a corpus of entity-linked sentences, where entity-linked just means that the entity spans have been identified in the strings. Any corpus that references the entities of interest may be used, and any entity linking methodology. We use a corpus built from a Wikipedia dump in 2019, and we regex the hyperlinked entities within that corpus. Taking a look at this example on the left, we have the mask is awarded by the Royal Astronomical Society for investigations of outstanding merit in theoretical physics. Here, we want the model to predict the entity that should go in the mask slot. That is Eddington Medal. So we want to assign a high probability to the unique identifier of Eddington Medal. For fine-tuning and evaluation, we work on cloze-style sentence templates that we create from the n-ary link prediction dataset. Any text representation of the n-ary query can be used, but linguistic alignment with the pre-training dataset may benefit performance. We simply space separate textual names of entities and roles. As we can see on the left here, we have Stephen Hawking award received mask point in time 1975, where it's subject, relation, object, role, qualifier entity, role qualifier entity, and so on, dependent on what order the relationship is. As we can see, this text is not that natural in structure and vocabulary, but the meaning is roughly maintained. The model we use is a BERT encoder architecture, though often we use something smaller than BERT base, with a linear decoder layer and softmax cross entropy. So looking at our results, we first of all evaluate on the WikiPeople dataset, and we introduce our own version of the WikiPeople dataset, which we call WikiPeople literal, which probes the ability of the model to interpret literal qualifiers, which are often ignored in the standard WikiPeople evaluation. Most of the qualifiers in WikiPeople are literals. Date times are in 12% of statements. Though, as I say, in the standard WikiPeople evaluation, literals are ignored, so only 2.6% of facts in WikiPeople are higher order. The baselines that we use, we have 5 external baselines, NALP fixed through GRAN. These all do not use natural language and all do not encode literals. We also have an ablation of our model called hyper-elk-unc, which replaces literal entities with the unc token such that no literal information is available to the model. In terms of our performance on WikiPeople literal, on the left of this table, we significantly outperform both stare and hyper-elk-unc, with the performance boost on the unc ablation illustrating that the model is using the literal information. We do not evaluate on high transformer or GRAN because high transformer didn't have a public repo and we struggled to run the GRAN repo. But as you can see in the standard WikiPeople evaluation on the right, they all perform similarly, and we hope that that would extrapolate. Looking at that evaluation on the right, the standard WikiPeople evaluation, we see that we outperform NALP fix, but underperform the more recent baselines. Having studied the predictions on this dataset versus stare, we find that the largest performance deficit is on one-to-many relationships with many possible answers. For example, mask, sex or gender male. There are lots of entities that fulfill the sex or gender male relationship. We hypothesized that the softmax loss function used in training language models may not be appropriate for this task, as it assumes a single correct entity for each training example, treating all competing entities, including valid ones, as false, of which there will be many for a sex or gender male relationship. So we think that a future direction that would be interesting would be looking into the objective function and the negative sampling approach that comes with it to improve performance on this style of relationship. Our second evaluation was on the WD50K dataset, which was introduced to have a higher proportion of hyperrelational facts than WikiPeople. As discussed, WikiPeople, when literals are involved, only has 2.6% hyperrelational facts. So the baselines that we use here are 2 ablations of our model, only P, which is only pre-trained, without any exposure to the fine-tuning dataset, and only F, which is randomly initialized and only fine-tuned without any exposure to the pre-training dataset. We also have a BERT plus fine-tuning model, which is a fine-tuned BERT model with the BERT base initialization. Looking at our performance on WD50K, we see that we're nearly identical to state-of-the-art, outperforming our BERT model as well. And on WD50K 100, which is a smaller, purely hyperrelational version of WD50K, it's kind of subset of WD50K, we see that we outperform BERT, are comparable to stare, but underperform high transformer, which is an improvement on stare. High transformer uses auxiliary masked qualifier prediction task, which we think will be particularly useful for this dataset because this dataset has a higher proportion of qualifiers and also is smaller. So having that auxiliary task will provide more signal. So we think looking into auxiliary training tasks and auxiliary components to the loss function may also be an interesting direction for future work. Now looking at our hyper-elk only P ablation, we see that without any access to a training knowledge graph, it significantly outperforms random. And it shows some ability to do this task. We think, again, that this will be particularly valuable in domains where curation of high quality, hyper-relational knowledge graphs is not feasible. Digging into that only P ablation to consider where the deficit to the non-ablated model might be. One place might be the distribution shift in language from pre-training sentences to the templated format that we use. The templates, as we saw at the beginning of this presentation, are often stilted and ungrammatical. So in this experiment, we look to align the template grammar more closely with the pre-training corpus. We consider the 37 most frequent roles and relationships, and we improve their grammar with simple changes such as including stop words like the. We see that this results in a significant performance increase on the only P ablation of about 3%, but when fine-tuning, this performance increase is nullified. This suggests that the model is adapting effectively to the templated linguistic style during fine-tuning. So to summarize, given all that, we are the first natural language-based approach to n-ary link prediction. We're the first approach to leverage literals in n-ary qualifiers, and we're the first approach that does not require an n-ary training set or knowledge graph to perform the task. We achieve state-of-the-art on the primary n-ary link prediction dataset, WD50K, and on WikiPeople facts that include literals. We outperform pre-trained models like BERT, even with a smaller model. And a reminder of the future work that we've mentioned previously, we think that looking into the objective function and negative sampling approach of our language model would be useful in order to combat these situations where there are one-to-many relationships that we perform poorly on. We think that it would also be interesting to look into auxiliary tasks and auxiliary loss functions in order to gain more signal when the relationships are higher order and the data sets are smaller. One final practical place for future work is in the entity linking methodology. So for your particular use case, you will potentially want to use a better entity linking methodology, potentially a neural entity linking methodology, in order to find more occurrences of your entities of interest in your given corpus, and to be more accurate about which occurrences you find. I want to thank you for your time and hope that you can find interesting research directions based upon our work.